In this video, I want us to step back a little bit and discuss why the above theorem about Taylor series is true. Of course, we do not need to discuss the case of Maclaurin series separately. Maclaurin series is just a particular case of a Taylor series with A, the center of the series, being 0. And so it suffices to only prove the above theorem for a general Taylor series. So how do we justify that theorem? Suppose, as we did in the theorem, that f of x is equal to the sum of an infinite power series centered at the number k, at the number a. So this series here looks like so. F of x is the sum c0 plus c1 x minus a to the first, or just x minus a, plus c2 x minus a squared plus c3 x minus a cubed, and so on. And so this representation, we assumed, holds for absolute value x minus a less than r. Right, so this was our assumption there, and let's say r is positive. Okay, so otherwise this is not exactly a meaningful representation, it's just representation at a single point. So let's say r is positive. Let us now determine the coefficients in the power series ck. So in order to do that, we can start by saying that, look, it is really easy to compute C0. So this is a really simple coefficient because, and that is what we want to start with anyways. So when x equals a, right? In other words, when we evaluate the f at the point a, then all these terms that contain x minus a as a factor will vanish, and we see that the only term in the infinite series here which will be non-zero at point a is the very first constant term. So f of a is precisely the c0. So at least we can compute one coefficient in this power series, the c0. It's really easy. We just plug in x equals a, and there we have it. Great. So how would we go about computing the subsequent coefficients? Well, we have just observed that c0 is simply the value of f at the point a. And so the other ck's play a similar role with respect to derivatives of f. Namely, since we can differentiate power series term by term, something we know from our previous discussion, we even had a theorem to this effect. What we're going to do is, let us differentiate this equation here with respect to x, or this one, because these are really the same. So let's differentiate this equation, which I will call star. This will be the equation star. So let's differentiate star with respect to x. By this I really mean let's differentiate both sides of of the equality star. So let's say star, specifically both sides of it, with respect to x. And let's see what that gives us. So we take star, the equality, and differentiate both sides with respect to x. On the left-hand side, we will just have the derivative of f. So we'll have derivative of f equals, now let's differentiate the right-hand side. As we know, we can just differentiate term by term, so the constant term will vanish. The only term, the first term that survives will be this linear term here. So by taking derivative of it, I will just have c1 plus, by taking derivative of this term here, using chain rule, I will have c2 times the derivative of this power here, so times 2x minus a times the derivative of the inner function, which is 1, and so this is the expression for the derivative, plus derivative of the third term, c3 times 3x minus a squared, and so on. So what we see is that the value of f prime at the point A is equal to c1, right? Because c1 is the constant term in this infinite power series. So if you plug in x equals a, these terms that contain x minus a as a factor will vanish, and we have therefore found a way to express c1 through the derivative of f at the point A. Great. So this seems to be the correct approach. So let us now differentiate both sides of this new equality we have for f prime of x. We know that differentiation does not change the radius of convergence, so this still holds for x minus a less than r, for the same r as we had in the previous equation star. So to continue on to the next coefficient, ck, let us take this equation, which we'll call double star, and do the same thing to it. So let's differentiate. Both sides of double star with respect to x. So that gives us, on the left hand side, the derivative of the derivative is the second derivative. On the right hand side, we have a bunch of terms. The constant term will vanish. The first term that survives is this one, which is now linear, so I will have 2c2, right? And then plus the derivative of this term, c3 times 3 times 2 times x minus a. So I took the derivative of x minus a squared, which gave me this 2 over here, and then I had to lower the degree of x minus a to 1. And so this is the derivative of the second of the square of the second order term rather in this series. And then I have all the subsequent terms in which I'm not yet interested. So let's see what this equality here implies. If I evaluate the second derivative of f at the point A, I will have 2c2, because all the subsequent terms contain x minus a as a factor and therefore will vanish. And so this implies that c2 is equal to f double prime of a divided by 2, right? In the same spirit, but rather uselessly, we can rewrite the previous equation as c1 is equal to f prime of a divided by 1, right? So this is equivalent to the equation we had for c1, and it has the same form as the equation we obtained here for c2, right? Great. And you can see that this process can continue. So we can do the same to this new equation, which we can denote triple star. So differentiate the triple star now with respect to x. So as you can expect, this will result in a new equation which will contain the third derivative of f, and it will give us access to c3. So with respect to x. I should probably note before I do this that the equation triple star also holds for absolute value x minus a less than r, because it has the same radius of convergence as the equation double star, and we know differentiation of power series does not change the radius of convergence, and that is why I have the same radius of convergence for this new equation as well. And finally, differentiation here gives us the third derivative on the left equals, here only the linear term survives, the constant term cancels, and then I have the higher order terms. So I will have c3 times 3 times 2, I could say times 1, which is what I obtain by differentiating x minus a. If I differentiate x minus a, I get 1, and then plus the higher order terms. And so from here, we see that the third derivative, evaluated at point A, will be equal to this constant term here, because all the higher order terms contain x minus a as a factor, right? So all of these terms contain x minus a. When I plug in a for x, only the constant term survives, just the same way as it was for the previous equation. And so I will have f triple prime of a equals 3 factorial times c3. So it is useful at this point to recall that this product here has a special notation 3 factorial. And so as a result, we have this formula for c3. We have c3 is equal to the third derivative of a divided by 3 factorial. And you see that this has exactly the form this formula has exactly the form that we had for ck in our theorem about Taylor series. Exactly the expression we had in here. So compare these two. We see that they are exactly the same. And now we conclude this proof by saying, well, differentiating f of x and its power series k times, right? So what we did so far was we differentiated it once, then twice, then 3 times. And if we do it k times, we will obtain that ck is equal to the kth derivative of f at the point A divided by k factorial in exactly the same way we did it over here. And so this gives the formula from the theorem, and this completes our justification of the theorem about Taylor series. So to summarize what we did here, we said suppose that f of x can be represented as a power series of this form with some positive radius of convergence, then C0 can be determined by just taking f of a. C1 can be obtained by evaluating f prime at a, and so on. C2 can be evaluated by taking f double prime at a and divided by 2. There's a similar formula for C3 and so on. The general CK is given by this formula, and that is precisely what our theorem tells us. So, in general, the result of the theorem follows from our ability to differentiate power series term by term with conservation of the convergence radius. And so that completes the proof of our theorem.